All right, welcome to Physics 2110. I am Mr. Wade or Professor Wade, just not Dr. Wade. Sorry, again, we have to meet, quote unquote, like this for the first time. And apologies in advance if I cough or have a little bit of brain fog during this. But anyway, we'll go ahead and get going. So the main things that I want to point out here are where my office is. If you enter Manning Hall from the main entrance, you just take a right, and I believe, the second door after the elevator on the right. So if you have any questions, feel free to drop by any time. My actual office hours are every day from 12:30 to 2, but if I don't look too busy, usually you can drop in at other times. Our textbook, I'm going to show you how to get connected to that here in just a minute. And then again, the course FAQ is the other big thing I want you to read, and I'll show you where that is in a second as well. The only other thing I want to point out from the syllabus is this one, highlighted in red. So we do have quizzes every week. They're not pop quizzes. You'll know when they are. It's every time we complete a chapter. The next class will have a quiz over that chapter. It's very short, and it's meant to be pretty low stakes, but it really brings things to a halt if you aren't timely about making up quizzes. And this is my one thing, my one pet peeve is if you are not able to make it to a quiz, let me know over email and you'll be able to make it up no problem, but you have to let me know. It can be an email as short as, I'm late, or can't make it today. You don't have to explain why. You just have to let me know before the class happens over email. And it could even be that you're running late and you get in the door and you see me picking up the quizzes. Send an email right then and say, I'm late, but I need some sort of record to be able to let you make up the quiz at a later time, and to please make it up as quickly as possible. Okay, everything else I'll let you read through on your own time. Next thing, again, we'll say how to get connected over here real fast. So I'm in the student view for the course right now. On the main page is where you'll see the FAQ. So just read through that. And then there's a couple other things. The Physics 1010 notes are just for an introductory physics class that I teach. If you want sort of a soft, no math introduction to some of the concepts we'll be going through, it's not as detailed as what we'll be talking about, but it may help give a better feel for some of the ideas without having to get too deep into the math. To connect to the textbook and for all of your assignments, you're going to go to Wiley Course Resources on the left. It will ask you to create an account, or if for whatever reason you already have one, to sign in. Once you do that, the only reason you'll ever have to go to this link is to go to the textbook. You click launch right there. And I have not made these practice things myself, but you can do these practice questions here if you like. And there's some other resources in the course resources. But for everything else, for all assignments, they will just be on Canvas. So for instance, down here, once we have our first assignment, which will be once we finish this first chapter, there will be an assignment in the chapter 1 module, and then keep going like that with 2, 3, and so on. If you have any questions or any issues with getting connected to Wiley, let me know, but please do that as soon as possible, just because it helps set things up and not cause an issue at the Smart Start opt-out deadline. Speaking of that, if you are in Smart Start, that's it, no problem. If you are not in Smart Start or you opt out, you will eventually be signed out and you'll have to pay for an access code, but you also do that through the Wiley Course Resources link. Next thing, I need to show you my dog. So this is Toji. This is a stamp I have of him. I have a good physics Toji and a great physics Toji. So for those quizzes, they're 5 questions. If you get 5 out of 5, that's a great physics. If you get 4 out of 5, that's a good physics. For exams, if you get a 90 or higher, it's a great physics. 80 to 90, it's a good physics. Here is the actual Toji. And I do have another dog, Mina, that you'll see probably on exams and things. I just don't have stamps for her yet because she is newer than Toji. Now, this I've not sent out notes for because you really don't need it in the long run. I just want to give you some feel for why you might care about physics, and the best I can do to do that is to tell you why I care. So, I'll talk a little bit about the research I did as a graduate student. I don't do research now. It's not my favorite thing, but I do feel like I got a lot of takeaways from doing it in graduate school. So I researched sonic booms, and I want you to think if you've ever heard a sonic boom. If your answer is yes, I can guess where. Maybe at an air show, maybe you're affiliated with the military, or, and this is the least likely, some sort of academic research thing, although that's where I experienced them. So the reason for that is because sonic booms are actually illegal over land and have been since 1973. The reason for that is they're just really loud. They sound a lot like a gunshot not too far from your ear. And so in the 60s, you had sonic booms going off all the time. People got sick of it. They called into the FAA, and eventually it was banned. So, why would we be researching sonic booms then? Because for ever since then, we've been trying to figure out how to bring them back. And of course, the obvious way is, well, you got to make it quieter. So, how do you do that? And to understand that, I first got to tell you what a sonic boom is. Over on the far left, I've got a plane, and it is flying at a what you call subsonic speed, or a Mach number, that's what M is, of less than 1. All that means is its speed is slower than the speed of sound. Reason that's important is if you imagine sound is going out in all directions, that's what these sort of bubbles are around the plane. And this is sort of an idealization, but we just pretend it's spreading out equally in all directions. The largest bubble is sound that was generated a while ago. The smallest bubble is sound that was just generated by the jet. And since the jet is flying slower than that sound, the bubbles have sort of a chance to spread out away before the next one is generated. That changes once we get to the speed of sound, or a Mach number of 1, because then the jet is keeping up with the sound it's producing, and that causes these bubbles, these compressions of air, to bunch up along this line right here. And that causes a lot of drag on the jet. This is why you sometimes hear this called the sound barrier. But if the plane manages to make it through that sound barrier, it goes faster than the speed of sound, supersonic, or a Mach number greater than 1. It gets ahead of the sound it generated. So this bubble was sound generated a while ago. It is past that. And instead of bunching up along a line, the sound, the compressed air, bunches up along this cone. It's called a Mach cone. And the stuff you're seeing here is just how you would find the angle that cone makes. The important thing is the faster the plane goes, the narrower the cone gets, because the plane is getting further and further ahead of the old sound waves. So what I studied as a graduate student was something even worse than that, something even louder than a sonic boom. So this is what you eventually hear on the ground. It just travels down and down and down, and eventually someone hears it. So that's already like a gunshot, is what that sounds like. I studied something called a super boom, or focused sonic boom. And that happens when, one case where it happens is when a supersonic jet accelerates, so speeds up in this case. Reason for that is, we said the faster the plane goes, the narrower the cone gets. So this is supersonic. It's already going faster than the speed of sound in that first picture, but it's getting even faster, and that angle's getting narrower and narrower. What that does is, those sound waves, the cone that's sort of spreading out away from the jet, end up bunching up again. So it's already bunched up sound waves, but then they converge to this even more bunched up region we call a caustic. It's called a caustic because it's like focusing of light, and focusing of light can burn things. It is caustic. What you would hear if you were around this surface is something like a gunshot, but now right beside your ear. So it can cause permanent hearing damage. The problem is it's unavoidable. If you ever want to go supersonic, if you ever want to get up to a supersonic cruise speed, you got to do this. You have to accelerate. So, if these are illegal, regular old sonic booms, how illegal do you think super booms are? And so that's a problem that has to be considered to try and bring back supersonic flight. What has been done in the past 50 years or so is a model has been developed for this scenario where a plane is accelerating. And we've gotten to where we have a pretty good idea of how it works. Part of that was doing a bunch of flight tests. So NASA conducted tests like these, several over the past few decades, but this is one from 2011. And so what they do is they have a bunch of microphones on the ground to try and capture every bit of this super boom event. And so it's going to be loudest on this caustic where all those waves are bunching up. And that's really the prime region of interest. But there's also some other areas to look at. If you get past that point, this will be where the plane reaches its cruise speed. It's just regular sonic booms. So not super interesting, still very loud, but we know how that works pretty well. What is kind of interesting is before that first touchdown of the caustic on the ground, you get what's called the shadow zone. And it's because the math predicts, at least on a first pass, that you hear nothing there. It's completely silent. What it actually sounds like, and if you do a little bit more math, it'll predict this, is like distant sort of rolling thunder. So it is much quieter, but it's sort of interesting how it goes quiet, 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 very, 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 very loud, and then very loud. This red box is what took so long for us to understand how to model. The first pass at it was in the 60s, and we've still been trying to add on and build to the model to this day. That was what my research was to add on some effects, account for some additional features of this region. So before I came in, where this model was it accounted for the focusing of sound. It also accounted for the fact that wind could be blowing in this region, and that moves the air around, so convex sound. It also accounts for the fact the air can absorb some of that energy, and it accounts for that loud sounds actually behave a little bit differently than quiet sounds physically. All of that gets mashed up into what we call a model equation for the scenario, and solving that equation tells us about the pressure inside this box, so what it would sound like there. Brace yourself for the equation. This is called the lossy nonlinear Tricomi equation, and my job was actually to make it even worse by adding a line to account for what you can't really see in this picture because it looks like a 2D slice, but what happens off to the sides of the jet, not just directly beneath it. And so that added a whole bunch of stuff down here. Take it in for a second, realize how nasty it is, but then realize that this is our best guess at how things work inside of that red box. And so what we did is we saw what this model spit out, and bear in mind, this is not something anyone can solve. You can't do some algebra and eventually solve for P, that's the goal here, the pressure, and get something. You have to put it into a computer and do essentially a glorified form of guess and check. And not just any computer, this would be something you'd run on one of NASA's supercomputing clusters, and it might take an hour to spit out an answer. But when they did that and compared it to that flight test that was run back in 2011, they got some plots like these. Blue is what that equation spits out. Red is what they actually measured during that flight test. And what you might notice is it's actually doing pretty good. That model is. It's looking at if Z bar is a positive number, that's you're up above the caustic, so you're in this region. Use a different color here. You're up here. If Z bar is equal to 0, you're right near the caustic, so you'll see the pressures are very high there. And if Z bar is negative, you're in this shadow zone, so you should see much lower pressures. And that's what happens here. So above the caustic, the peak pressure is around 100 pascals. You don't have to worry about what pascals are at this point. But as we get close to the caustic, you can see the peak goes up to, the measured peak was almost 3 times that. And then the model spits out something maybe 2.5 times as large as we saw up here. Below the caustic, much quieter. It's maybe about half the intensity of what we saw up above. The other thing to notice, though, is while the model does pretty well, it's not perfect. So as complicated as that equation is, it still doesn't account for everything. So why would we do this? It already sort of seems like a losing battle because it's so loud, sonic booms are so loud they're illegal. What could we hope to do to make them quieter? And so what many organizations, but what NASA has in particular been working on for ever since supersonic flight was banned, was a quieter sonic boom, a jet that produces one. And the only way they've found to do that, at least reliably, is to change the shape of the plane itself. Reason being, when I said that it generates one Mach cone, I kind of lied. It actually generates Mach cones at every point along the surface of the jet where you have a sudden jump in the shape of the plane. But what usually happens is, as that sound travels down towards the ground, eventually all of those bunch up into one big Mach cone at the front of the plane and one big Mach cone at the back of the plane. And those are what you hear as a da-dum. That's the sonic boom. Usually they're so close that it sounds like one big boom, but it's actually two. And that's the same for a gunshot. A gunshot actually is a little mini sonic boom. The bullet is just so small that you really can't hear those two separate bangs that make up the sonic boom. So here is the proposed plane, at least as a proof of concept for this idea. You can see that it's very thin, it's very sort of spread out, and that's the idea. That will spread out those shock waves and ideally stack them up in a way that makes them sound quieter by the time they reach the ground. It's called the X-59 because it's NASA's 59th experimental plane. Quest is quiet supersonic technology. This is just a 3D render, but what you'll notice is, in addition to the sort of weird shape and very long nose of the plane, it has no window. Reason being, the shape of this plane is so important, they had to sacrifice a window. Instead, they've got a camera system in there, and that just reflects what's going on outside to the pilot. So you have to hope that that camera never fails. So when you look at this, it's a 3D rendering. And so you might think this is a very futuristic sort of thing, like this is not coming out anytime soon. It turns out this already exists. They have made this jet, and it is actually even flown. It's not done the big test flight to where it will demonstrate how quiet it's supposed to be, but it's very close to that. And I've been saying that for years, but this time it really has flown. Once it does that first test, where it's really trying to demonstrate that it is a quieter sonic boom, they predict that that sonic boom, in comparison to the usual ones, which again sound like gunshots, this will sound like a car door shutting from about 20 feet away. So just a little thump. They actually call it a sonic thump. So if that's true, if it works out that way, that is a huge leap forward. It'll still take a lot of work to turn that into something we could ride in someday, but that's the goal. And I don't know if you realize, most commercial flights now, they never make it past maybe Mach 0.7. This one's designed to go Mach 1.5 at cruise. So imagine any flight you've ever taken, taking half the time. That's what they're going for. And that's useful not just for general travel, but for if you have an organ transplant, you need to get that organ across the country as fast as possible. Put it in this. So I'll show you NASA's video of its first flight. Again, this does not demonstrate that sonic thump. It's just, it demonstrates that the plane doesn't fall apart. But it's cool to see it finally fly.
In the room, we are on card 1. We've just received takeoff checks and takeoff briefs. We need the control room poll. This is going to be a verbal from the leads. Starting over here with Zeus.
Zeus, go for takeoff.
UCS, go.
Fuel is go. Prop go.
BMS, go.
Air data, go.
FQ, go.
Avionics, go. Flutter, go.
Hydro, go.
Flags, go. Loads, go. SOR, go.
GD, go.
Control copies all. X-59 control is go for takeoff.
Right. So the X59 is actually very close to showing this proof of concept that you can make a quieter sonic boom. And the hope is in the next maybe 20 years or so, we will be able to have much faster flights than we ever did before. So let's kind of recap. So if we look back, this is a pretty complicated thing to understand. But if we keep building on it and we keep working for, in this case, decades, we can start to understand how this works a little bit better, although it can be very complicated at the end. What's more interesting than that, though, is despite how complicated this looks, whatever nature is doing is still better, is still more complicated, is still something that we don't know how to model, don't know how to handle all those disagreements. But even with that still somewhat limited understanding, we can develop new technology, develop things for the betterment of humanity. That's why I like physics. First thing is, it's happening. And by the end of the course, the hope is you will see it happening around you a lot more, notice it a lot more. And you can shut that out if you want, but I mean, that's sort of like ignoring light or ignoring sounds. Like, it's there. You kind of got to look at it. The next thing is it lets us understand nature better. Now, you may not consider this nature, but it's sound. Okay. And this applies to not just jets, it applies to any sort of loud sound. But it also shows if we study long enough that nature is always smarter. Even the most complicated models we have to describe the most fundamental building blocks of reality, they still have issues. They still don't fully describe everything that happens. And that's just the continuing pursuit of science. So, regardless of your religious beliefs, that's interesting. That there is this thing that no matter what, it will always compute these things faster than you. It doesn't need a supercomputer and take an hour to spit out an answer, and sometimes that answer's wrong. It just does it in real time, no matter how complicated the situation is. You know, you want to fire a rocket at this thing while it's flying and doing all this stuff. You want to crash something else into it. No problem for nature. For us, that would take another 20 years of modeling to incorporate that. It also lets us create new technology. And in a way, it lets us predict the future. NASA is very confident that this thing will sound like a car door shutting, even though up until earlier this year, it had never flown before. And up until the past couple years, it didn't exist. And yet they've been confident it will sound like that for a long time now. And it's because they have these physical models that predict these things accurately enough that we can feel confident in making these claims even before the technology ever exists. With that in mind, we're going to pivot to the actual course. What you have to keep in mind is the course is not going to feel like this. It's not always going to feel interesting and cool and like you're seeing behind the scenes of reality. Sometimes it'll just feel like I'm talking about dropping a ball for the 20th time this semester. The reason we have to do that is because to understand these very complicated things, I mean, this took me years. That was 4 years of my life to understand what this even meant. You got to understand the basics. You got to understand motion and all these things that go along with it. So think of Physics 1 as the eating your vegetables of physics. It's not why anyone does physics, but everyone who does physics did Physics 1. All right, so with that, let's get into it. So, what is physics in the first place? It's the study of things like sound, like light, all these things that are very fundamental. So, physics is the study of basic things, things that are fundamental to understanding the world around us. So, things like motion, things like forces, things like energy or momentum. And so you may say, well, what exactly does basic mean? And the best way I can put it is think for a second, what is your definition of energy? What is your definition of force? And you may have one. You may say for energy, well, it's the ability to do work. But then I ask, okay, so what's work? If you say, well, it is a transfer of energy, well, then you've got a circular definition and you still haven't defined anything. If you maybe took a physics course and said, well, okay, but work is the effect of a force over distance. I say, great. Okay, so what's a force? Well, it is what causes the mass to accelerate. And I say, okay, great. What's mass? Eventually, I will get you somewhere along the line, and you can't define things anymore. You run out of words to say about it. And that's what physics is trying to delve into, is what are these things? So let's keep going. Could be things like electricity, or magnetism, or light, or sound, or heat. Or we zoom way in, we look at the atomic structure. And roughly, the stuff over here to the left is what we'll look at this semester. The stuff right here, you'll look at in 2120, the second semester. If you decide to major or minor in physics, that's where we cover the last of this stuff, 2130. And then the upper level physics is sort of going back around and adding even more details and even more complicated interactions to all of these things. And you just keep building like that in layers. That's the things we're going to study, and the rest of this chapter is just about the baseline stuff we need to know to be able to study those things. First thing we got to do in physics is take measurements. And in order to do that, you need to have a standard way to measure things, like measure in terms of something else. You know, you have a ruler, but until we decided what an inch was, we didn't know what to put on the ruler. So let's look at the quantities that we will be interested in and how we measure them. In physics, we pretty much exclusively use SI, the System International. So every other country in the world besides the United States, and maybe I think there's one tiny country somewhere that does the imperial system still besides us, but every other country uses SI. And it's because it makes a lot more sense than what we use. The SI system has come up with 7 base units and base quantities that you can build any other unit, any other quantity out of. So quantity is just a thing you're trying to measure. A unit is what you use to measure it with. And the unit is defined in terms of some standard, some observable thing. And we decide that is a second. That is what we're going to call a foot or a meter or whatever else. We call them base quantities because you can't pare them down any lower than these 7 if you want to describe everything we've observed. You cut one of these, you will have some things in nature that you can't describe. So base quantities are the quantities which can't be expressed in terms of each other. And we measure each of them with a base unit. So the base unit for time, for instance, is the second, abbreviated S. Base unit for mass you might think is the gram. In the SI system, it's actually the kilogram. Base unit for length is the meter. For current is the ampere, or amp. For temperature is Kelvin. For amount of stuff, this is probably more familiar from chemistry, but the mole is a standard amount of something. And luminous intensity, just think brightness, is the candela. That doesn't mean you're going to see all of these show up regularly. In fact, in this semester, we're only ever going to see these 3. But you could talk about any physical quantity in terms of these 7. So you have to ask, what is a second? And nowadays, it is specifically defined to be the time it takes for that many oscillations of light. So light has a frequency associated with it, that many oscillations emitted as you give a cesium-133 atom some little amount of energy. As it releases that energy, the electrons within it go down to a lower energy level. They emit that energy at a certain frequency as light. How long does it take for that many oscillations of that light to occur? That's a second. And you might think that's a pretty useless definition, and it is because it is to most everyday normal human beings. The reason it's a good definition, though, is because it's defined strictly in terms of things we have no control over. Cesium-133 is going to emit light this way when given energy, no matter what. It is a physical sort of constant of nature. And so we define the second to be in terms of these physical things. Was the second always defined like that? Absolutely not, because we didn't even know to do experiments like this when we first defined the second. But we've refined the definition over time to be in terms of very precise things that are very predictable. Similar for kilogram, that one's a little bit more technical because it has to do with this relationship between mass and energy, but it has its own definition. And then the meter, again, is defined in terms of pretty fundamental things. It is how far light travels in vacuum in this fraction of a second. And there's similar things for the other four. From now on, you can forget that forever. You have a natural feel for what a second, a kilogram, a meter are. Those are just the strict technical definitions. And by the way, the reason the SI system uses the kilogram instead of the gram is because it tries to pick human units. It is very hard to tell the difference between a gram and 2 grams just from them sitting in your hand. You can tell the difference pretty easily between a kilogram and 2 kilograms. So we defined the grams way back when, but then we picked the kilogram as the representative unit for the SI system because it's more human. Similar for the meter, about 3 feet. We know roughly how long that is, and a second, we have a feel for how long a second is. Ampere, you really only have a feel for how large that is because that's roughly what it takes to kill a person. But we'll get to that in physics too. Okay, so now that you've got your base 7 units, you can start building other units out of them. You call them derived units. And to do that, you just take 2 or more of your base units and smack them together. So, for instance, a Newton is a measure of force. It is the force needed to give a 1 kilogram mass a 1 meter per second acceleration. So to make it gain 1 meter per second of speed per each second that passes. Abbreviated 1 Newton is 1 kilogram, meter, and per second, we abbreviate a lot as second squared. Okay, and we'll get back to forces a little bit down the road, but the idea is we can use these base units as building blocks for any other unit. However, if we strictly stick to always using kilograms, meters, and seconds, it starts to get a little bit unwieldy to measure certain things because it would just take so many meters to measure or so many kilograms or so many whatever else. So we come up with both scientific notation and prefixes. And hopefully these are both familiar, so I'll go through this kind of quick. But idea of scientific notation is you want to write the number as first digit, then a decimal, and then times some power of 10. So for instance, the radius of Earth is a lot of meters. That's a mouthful to say. But we could realize that if we wanted to write it as 6.378, the actual number is 1, 2, 3, 4, 5, 6 decimal places larger. So it is 10 to the 6 times larger than 6.378. So we could write that as 6.378 times 10 to the 6 meters. And that would be the scientific notation for that. Alternatively, you could realize, well, 10 to the 6 meters, there's a standard prefix for that. We use mega for 10 to the 6. So you could call this 6.378 megameters. Or if you wanted to get a little bit trickier with the exponents, you could realize 10 to the 6th is 10 to the 3 multiplied by 10 to the 3. So this could be written 6.378 times 10 to the 3 times 10 to the 3 meters. But then 10 to the 3 is also a standard prefix, it's kilo. So this is kilometers. And 6.378 times 10 to the 3 is just 6,378. All right, we could go the other way, very small quantities. So the mass of an eyelash. If we wanted to write this as 7 times 10 to the something, well, we'd have to take that decimal place and move it back 1, 2, 3, 4, 5, 6, 7, 8 times. So 8 times backwards, 7 times 10 to the negative 8 kilograms. The general rule of thumb is if it's a big number, it's a positive exponent. If it's a very small number, you're expecting to see a negative exponent. All right, but we could write this in a multitude of ways. Kilo, again, is 10 to the 3. So this is also 7 times 10 to the negative 8 times 10 to the 3 grams, kilograms. And so you could write this as, well, it's 7 times 10 to the negative 5 if I add that negative 8 and 3 exponent. 7 times 10 to the negative 5 grams. Or again, if you want it to be a little bit trickier, 10 to the negative 5 is the same thing as I multiply by 10 and then multiply by 10 to the negative 6, right? Because 10 is 10 to the first power, and then multiply by 10 to the negative 6, that's a minus 5 exponent. Well, what is 10 to the negative 6? It's micro. So this is 70 micrograms. And all of those are technically equally correct. It's just usually you want it to look the cleanest, and that'll either be you don't want any exponents if you don't like scientific notation so much, or the cleanest way would be in scientific notation, depending on your preference. We'll show an easier way to do this conversion once we get to unit conversion in just a minute, but that's just to show lots of different ways you could write these quantities. And if you ever look at your calculator and you wonder what the difference is between scientific notation mode and engineering notation mode, because usually it has both, engineering notation is always trying to get to the nearest power of 3 because that's what's standard in the prefixes. Scientific notation is just trying to get down to this something times 10 to the anything form. It doesn't care about just the ones that match up with a prefix. All right, unit conversion. Again, hopefully familiar, so we'll go through it sort of fast, but I'll start with a really simple question and see how you would answer it in your head. So how many seconds are in 2 hours? You probably could answer that in your head. So maybe you got the 2 hours is the same as 7,200 seconds. But you have to look at that and that equals sign and realize something's a little bit weird here. How is 2 equal to 7,200? And you realize it's not. 2 hours is equivalent to 7,200 seconds. So the units are just as important as the number to specify these quantities. And that also means you should be able to sort of work with the units in a similar way to the numbers to get from one side to the other. So you probably did multiply by 60 and then by 60 to get to this. And that makes the numbers work out. 2 times 60 times 60 is 7,200, but it does not make the units come out right. So I have to think about how do I get from hours to seconds on the other side. And all I have to do is just be a little bit more careful about how I did this calculation. It's not just times 60. It's realizing that there are 60 minutes in 1 hour. And then realizing that there are 60 seconds in 1 minute. And now, if we look across, we see I'm taking hours and dividing by hours, so those cancel out. Taking minutes and dividing by minutes, those cancel out. What am I left with? Seconds. So now both the number and the units work out. We call these things that we multiply by, so everything in parentheses, we call those conversion factors. And you can see that if we multiply those two things together, we actually get a new conversion factor that takes us directly from hours to seconds, or vice versa. Because 60 times 60 is 3,600. Minutes cancel with minutes. 3,600 seconds per 1 hour is another way we could write that. And that's useful because now you don't have to do 2 conversions for this. You just have to do this one. And you can add that to your bank of conversions. The strict definition of a conversion factor sounds a little bit more abstract. It's a ratio of units equal to 1. But it's not as weird as it sounds. 60 minutes and 1 hour are the same thing. They represent the same thing. What do you get when you divide something by itself? 1. That is equal to 1. And up here, although it looks weird to say it this way, it is 2 hours times 1 times 1 equals 7,200 seconds. But that's just because, again, these two represent the same exact thing. You're just expressing it in a different way. And so I like to think of unit conversion as sort of like translation. You're just expressing one thing in terms of another language, even though they're both representing the same thing. Okay, 2 hours and 7,200 seconds are the exact same thing. They represent the same thing, just different ways of putting it. And so the process of converting units is sort of similar to translation. You think about what your input is, what you want to translate. You think about what's going to take you from that input to that output. You look up some sort of conversion between the two, and then you use that to get your output. It's a little bit more technical for conversions because we have to do numbers, but that's the idea. So let's do a slightly harder example here. Convert 20 meters per second to miles per hour, noting that 1 mile is 1.61 kilometers. My input here is 20 meters per second. And I'm going to write it like that as a fraction because that makes this cancellation of units a little bit clearer. My output that I want is miles per hour. What things can I multiply by to ultimately get something in miles per hour? And depending on if you've taken chemistry or seen it somewhere else, you may have seen this where you sort of make a grid here. That's fine if you prefer to do it that way. The idea there is so you can sort of see that if a meter is up top, you'll want to have it down bottom at some point so they cancel out. If seconds is down bottom, you'll want to have it up top at some point so they cancel out. I'm just going to go through it a little bit more step by step to see how we think through this. But if you like that way better, feel free to do that. I want to take in meters and get miles out the other side. I need to think about what I know I can do with meters at this stage. I know I can put meters in terms of kilometers because I've got my prefixes up here. But then it tells me how I can put kilometers in terms of miles. So that's sort of my first chain of reasoning is I want to get rid of meters and get kilometers out, and then get rid of kilometers to get miles out. So if I want to get rid of meters, it should be in the bottom, so it cancels with this meters up top. I want to get kilometers out, and now that I've written the units, it's easy to get the numbers right, to not put the wrong thing in the numerator or denominator. I look up here, I say a kilometer is 10 to the 3 or 1,000 meters. It's very easy if you don't do this step of writing the units down first to say 1,000 over 1, but that would be incorrect. The other check you can say, or you can do is say it out loud. 1 kilometer is 1,000 meters. It would sound weird if you said 1,000 kilometers is 1 meter. So you would know, you would have it backwards that way. Okay, now I need to get rid of kilometers. So it should go down bottom. And I need to get miles out. So kilometers needs to cancel. And then I look at what's given up here. 1 mile is equivalent to 1.61 kilometers. And now I'm left with miles up top, so I'm almost there. I just need to take seconds and get hours out. So what conversion can I do to get rid of seconds? And again, be careful here. If I'm getting rid of seconds, but they were down bottom at first, they better be up top now. And I want to end up with hours. So how many seconds are in an hour? Well, we just did that in the last question. 3,600 seconds in 1 hour. If we multiply all those things across, we get 44.7 miles per hour. And just like with this previous example, I could multiply all my conversion factors together to get a new conversion factor that takes me directly from meters per second to miles per hour. 3,600 over 1,000 and then over 1.61. That is 2.236. And then the units, it is sort of a jumble, so just take my word on this. Miles per hour per meter per second. Reason I know it's that is, again, because I want to take a meters per second number and multiply it by this thing to get rid of meters per second and spit out miles per hour. And now you never have to do that long conversion again. You have the shortcut. Take your meters per second number, multiply by 2.236. Another very tedious thing that technically you should worry about, but in this class I'm not very worried about, is significant figures. Reason being, there's already so many things that can go wrong in physics. You don't need one more that's just making things more confusing. So sig figs are not required in the class, but the homework, the Wiley assignments do at least want a certain number of decimal places. So just always maintain maybe 3 or 4 decimal places and never round in between calculations for homework problems, but you don't have to report a strict number of sig figs. I am still legally obligated to tell you about them though, so we're going to do this real fast, and this is almost a word-for-word plagiarism from Wikipedia because I just am not that concerned with sig figs. But anyway, we'll go through it real fast. The idea of sig figs is pretty clear. It's just the explanation of them is not always. The idea of sig figs is you're telling someone about the measurement you took, and you are expressing it in a way that reflects how confident you are in the measurement. If you just barely held up a ruler to something and eyeballed it, you're not very confident. You might report it to the nearest inch. If you really looked close and strained your eyes and said, I did this down to a 1/16 of an inch, you're going to take the time to report those extra digits. So that's what significance is, how confident you are in your measurement. And so really the way to understand this is think about the psychology of the person writing the number down. For instance, 91. They chose to write a 9 and a 1. They could have written 100. That would have been a pretty loose rounding, but they chose to write these individual digits. It has 2 sig figs. Both are numbers they chose to report. 123.45 has 5. So any number other than 0, it is a significant figure. Zeros are more confusing because sometimes they do show up just as sort of placeholders. So, for instance, if I have leading zeros, those first few zeros are not because I wanted to make sure you knew about them. It's because I measured something really tiny in the scale I was using, and in order to get to the numbers I actually saw, I actually read off on the scale, I gotta account for these decimal places. So they're not reflecting that I'm confident in those numbers so much as I had to write them to write the numbers I am confident in. So this has only 2 sig figs. And that might seem a little odd because you're like, well, it's a decimal and you're going to a lot of decimal places. That seems like you're pretty confident. This is actually the opposite. This means I used a bad measurement tool to take this measurement. This is you taking a ruler and using it to measure the width of a human hair. It's a bad measurement device. If you had a good measurement device, it would probably be in micrometers in the first place, and then it would be 340 micrometers, micrometers. So Usually 0.00, it actually means a bad measurement tool was used in the first place. All right, zeros between, those are easy. If it's between regular old numbers, it is significant because, again, you had to choose to report a 0 and not round off at that 0. You chose to write it down. It is a value you actually read off of the scale. So a number like this, regular digits, already count. So that's 5 already. This is significant because it's between regular digits. These two are also significant because, again, these are numbers like you read off of whatever scale you were using to measure this thing. They are not due to you rounded at a certain point or you had to report zeros before you could report the numbers you measured. So this has 8. The hardest one is zeros at the end of something. So if the number has a decimal point, those trailing zeros are significant because I could have just cut things off here at 1.2. But no, I looked real close at my measurement device and saw I'm not only confident in that 1.2, I'm confident that there is nothing in the hundredths place of this measurement, no hundredth of an inch adding on to that 1.2. I'm also confident there's no thousandth of an inch added on. So I took a pretty precise measurement. I'm pretty confident in that measurement. So this has 4. What about this? Well, the leading zeros, again, are not significant because I just had to get those zeros out of the way to report the numbers I did read off my scale. And again, I'm using the wrong scale to measure this thing. Trailing 0 is significant because I said not only am I sure it's 0.098, I'm also sure there's no, what is that, a 10,000th of an inch? So I could have capped it there and said, I'm not sure about that last digit, but no, I said, I'm very sure that there is nothing in that 10,000th place. So this has 3. And 120.000. I could have called it a day at 120, but I said, no, I know it's 120 and there's no 10th of an inch place. But then I could have called it at 120.0, but I said, no, I also know there's no 100th of an inch. And I also know there's no 1,000th of an inch. I'm confident in all those numbers. This has 6 sig figs. The absolute hardest one, trailing zeros without a decimal. Say I measured 3,000 for something, 3,000 meters or something took 3,000 seconds. Think about the person who reported that. Were they saying that I only know that first number? I estimated to the nearest 1,000 meters? Or were they saying I know that it's 3 and there's no hundreds of meters, but I'm also not sure about those last tens of meters or ones of meters? So I am pretty sure it's anywhere from 3,000 to 3,099. But don't quote me on those last 2 digits. Or it could have been they're actually pretty confident about the first 3. But then they're saying that last number could have been anywhere from 0 to 9, anywhere from 3,000 to 3,009. But don't quote me on that last digit. I'm not confident on it. Or they could have said, no, I measured this and it was exactly 3,000. I know all of those digits. Just don't quote me on the tenths place. It could have been anywhere from 3,000.0 to 3,000.9. So just as written, you don't know how many significant figures this number has. Has anywhere from 1 to 4. And this is actually another benefit of scientific notation, is it gets rid of this ambiguity. Because think about whether I wrote this as 3 times 10 to the 4, or 3.0 times 10 to the 4, or 3.00 times 10 to the 4, or 3.000 times 10 to the 4. These are 4 different levels of confidence in this measurement. Just being confident on that first digit, then the first 2 digits, then the first 3, and then all 4 of them. So this has 1, this has 2, this has 3, and this has 4. And it's because that takes us back to this previous version of that rule. And last is, what if you're dealing with multiple numbers and combining them in various ways? You're only as good as your worst measurement, is the idea of this last one. The least number of significant figures determines the significant figures of everything else. So if you have one lazy measurement, it pollutes all the other measurements when you start to combine them. So for instance, if we have some value that we measured at 2.06, so that's 3 sig figs. We have some other value, 5.6, so that's 2 sig figs. We multiply them together. 2 times that number times that number. Raw multiplication gives 23.072. And we have to decide, where do we cap that measurement? How confident truly are we in it? And it might be tempting to look at that 2 right there and say, well, but that's only one significant figure. So should I just call this 20, cap it at the very first digit? And the answer is no, because that 2 was not a measurement. It's a number we multiplied by. It is the ideal mathematical constant 2. It is infinitely significant because it's not a measurement. It is just something that comes about because of the math. Pi is another common example. It is infinitely significant because we could report as many digits as we care to. It's not the thing limiting the quality of the measurement. What is limiting the quality is this measurement of b. It's only 2 sig figs, so we have to cap it at 2. So we call this 23 if we want to report correctly in terms of significant figures. 2 sig figs. All right, and now that we've gone through that, don't worry about it for the semester, but again, I have to tell you about it. All right, another tedious thing we got to go through is trigonometry. This one, though, is really important for the rest of physics and the rest of engineering. You're going to see trig so much. The nice thing is, if you took a whole course on trig, you actually only need 5% of it, if that. So the core things we'll need are what are sine, cosine, and tangent. So I'm going to give you my own version of how we came up with those. This is not historically accurate, but I'm just going to pretend it is. All right, so the ancient Greeks, here's the problem they wanted to solve. Given any right triangle whose long side is known, and we'll call that long side the hypotenuse. The reason it's called the hypotenuse, at least etymology-wise, seems to be it means something like stretching over, stretching under, and it's because you can think of the hypotenuse as like a rubber band that you stretched across from this end to this end of this right angle. But anyway, given any right triangle where I know that side length, what are the other two sides? And I'll call that the side adjacent to this angle the hypotenuse makes, and then this is the side opposite to that angle. So adjacent, I think, is just sort of a fancy word for touching that angle theta. Opposite, I remember it as it's the one over there. Got to go opposite the angle theta, over there. And so first smart observation they made is, I don't have to keep redoing this problem for all these different hypotenuse lengths if I just solve it once for a very specific hypotenuse length, a length of 1. Reason being, once I know those side lengths for this triangle with hypotenuse length 1, any other triangle is just a scaled up or down version of that triangle. And so I can sort of think of the proportions of those sides. So I'm going to give the opposite side of this triangle with hypotenuse length 1 a special name. I'm going to call that opposite side the sine. I'm going to call the adjacent side cosine. So those are just the special names we give for the side lengths if the hypotenuse has a length of 1. But it'll be sine of theta or cosine of theta because it depends on what that angle theta is. If theta gets larger, that hypotenuse sort of gets steeper, moves up to here. Those two side lengths change. They are functions of theta. But again, once I know those side lengths, I can find the side lengths for any larger or smaller triangle just by scaling. In particular, the ratio of this length to this length will always be the same as the ratio of this length to this length, because one is just a scaled up copy of the other. So I can write that down. Sine theta, ratio of that to 1, is the same as the ratio of the opposite side for that large triangle to its hypotenuse length. All right. Similarly for cosine, once I find that length, I can say, well, the ratio of that side to that tiny hypotenuse of length 1 is the same as the ratio of the adjacent side for the large triangle to its hypotenuse. So that's all you need to think of sine and cosine as. Sine is just the name we give for the side opposite the angle theta in a right triangle of hypotenuse length 1. Cosine is just the name we give for the adjacent side of that triangle. Now the problem is just coming up with values for every possible value of theta. So you imagine that as just a running table of values. Goes from 0 all the way to really 360, because you can go all the way around. But the other smart observation the Greeks made was you can stop at 90 degrees, because once you get past 90, you're over here, the triangles start repeating themselves. They're just reflected off to this side. Or once you get past 180, they're just reflected upside down, but it's the same triangles. So I just need to come up with values for those two side lengths, sine and cosine, all the way up to 90. And it's easy for a couple values. If theta is 0, that means I'm dealing with a horizontal line. Well, the hypotenuse, it's length 1, but it's the hypotenuse of a squished triangle. It's completely flattened out. So it has no vertical or opposite side length. It has no sine value, but it has all adjacent side length. It is fully cosine. In other words, sine of 0 is 0. Cosine of 0 is the entire length, 1. And similarly, once we get up to 90 degrees, now it's a completely vertical line. It's a squished triangle, but vertically. So it has all opposite side length, no adjacent side length. Sine of 90 is 1. Cosine of 90 is 0. For every value in between those, you got to get more creative. And that's the part that I'm really going to hand wave. There's lots of ways to come up with those values in between, but that's all you need to think of sine and cosine as. It's just this table of values for those possible side lengths. And that's a useful tool because then you can use it to find the side lengths for any triangle you want, any right triangle, just by scaling up or down this sort of special reference or unit triangle. All right, now what about tangent? Tangent is answering the question of what is the slope or steepness of that hypotenuse? How high up is it? Well, to find the slope of anything, you see how high up it goes over how far over it goes, the rise over the run. And you can do the same here, rise over run. But our little reference triangle is just as steep, meaning you could also calculate this from those values in your table, sine theta over cosine theta. So all tangent is the slope of that hypotenuse for any particular angle theta. So it also depends on the angle. If theta is 0, again, this is a horizontal line. It's flat. What's the slope of that? 0. Tangent of 0 is 0. If it is a vertical line, what's the slope of that? Well, it rises by some amount without going over at all, no run to it. So you might consider that infinitely steep. It's a vertical wall. So tangent of 90 degrees is, you can say, undefined, or it tends off to infinity. And this is where we get those rules. Sine over 1 is proportional to opposite over hypotenuse. That's our way of finding that opposite side length. I could say opposite is hypotenuse times sine of theta. Similarly, I can say the adjacent side for that large triangle, I can just find by taking the length of the large triangle's hypotenuse, multiplying it by cosine of theta, that value I pull from my table. And if I wanted to know the slope of that hypotenuse, I can again just use my table values to calculate it. So that's all trigonometry was developed for, is as a systematic way to look at any right triangle whatsoever just by knowing the values for this special triangle. The rest of it is just sort of fluff and identities on top of all that. And that's where your mnemonic comes from of sine is opposite over hypotenuse. So cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, toa, SOHCAHTOA. And that's the way we'll use trigonometry in this course is I'll have a lot of situations where I know one or two sides of the triangle and I need to find a third. Or I know a side and an angle and I need to find another side, or I need an angle and I know the sides. Trigonometry lets me do all of that in a systematic way. It shows up a lot more than you might think in physics. Okay, so what are the units of sine, cosine, or tangent? No units. Why? Because each is a ratio of two sides. It's meters over meters, or we'll see newtons over newtons, or it's just a ratio of identical units. And so those units, like with the unit conversion stuff, they cancel right out. So sine, cosine, tangent don't have any units. But their use, as we said, is I want to find one side of a right triangle. Maybe it's opposite side or its adjacent side when I know that angle theta and I know one of the other side lengths. If I know two side lengths, then I can use the Pythagorean theorem to find the third. It just says for any right triangle, the opposite side squared plus the adjacent side squared is equal to the length of the hypotenuse squared. A squared plus b squared equals c squared. Or for our little reference triangle, you would write that as sine squared theta plus cosine squared theta equals 1 squared, technically, but 1 squared is 1, and that's where that quote-unquote trig identity comes from. It's not really an identity, it just is the Pythagorean theorem applied to our little special reference triangle with hypotenuse length 1. Okay, so let's see how we might use trig in practice, and this will be the last thing I do for today. Let's see, we've got a large SUV. The front of the hood is 40 inches off the ground, so they're saying that right there is 40 inches. I might give that a name, call it H for height, 40 inches. When you sit in the driver's seat, you have to look 13 degrees downward to just see the road. What that means is if you look less than 13 degrees downward, you can see the road out far ahead of you. But as you look at a larger and larger angle down from the horizontal, eventually you reach a point where you run into the hood. If you try to go to any larger angle than that, you're blocked by the hood. You can't see the road down here. So there's that special point at which you can just see the road, and anything closer to you, you cannot see. So I think you might see where this is going. And that is 13 degrees down from the horizontal. So that would be my angle theta. This is H. How far in front of the hood does your line of sight first meet the road? So they're asking about this length, which I'll call D for distance. These are just my own names I'm picking for these. You can pick whatever you want. So I know this is a trigonometry problem because they're feeding me sides and angles, and then my job is just to hunt down the right triangle in the picture. And here you can pretty clearly see what it is. this triangle right here. And trigonometry says if I know one side, I can find another as long as I have an angle. But the angle's up here, it's not inside my triangle, so what can I do? Well, I can remember some other geometry which says if that angle is 13 degrees, this angle down here is also 13 degrees. You may remember that as alternate interior angles of parallel lines, or just sort of proof by look at it. This angle looks about the same as that angle, but geometrically it is true that they are the same. Okay, so really, I am just analyzing this right triangle. And the question is, if I know H, how can I find D? And to answer any question like that, you're just hunting for the right trig function, sine, cosine, or tangent, and then you're just pulling a value from that table, which in this case just means using your calculator to solve this problem. So I know the side opposite that 13-degree angle. I know that length. I want to know the side adjacent to the 13-degree angle. Which trig function relates the opposite and the adjacent sides? Tangent. Without necessarily knowing how to solve it just yet, I write that out. I say tangent of 13 degrees is equal to the opposite side length over the adjacent side length. And now it's just algebra to solve for that distance d. So I can multiply both sides by d, and then divide both sides by tangent of 13, because that will get d on its own. But just keep it neat. I'll just sort of jump ahead and say, all right, so d is h over tangent 13. If h is 40 inches, divide that by tangent of 13, which again is just a value in a table somewhere, I get 173.26 inches. If I wanted to be careful about my sig figs, there's really only one given. If it's 40 inches, it's still that ambiguity of is that 1 or 2. I'd say maybe it's just 1. So I might actually report this as 200, but I don't care so much about sig figs. I'd rather get a number that is a little bit more representative of the actual value here. But I do want to convert that to feet, just so it's a little bit clearer what this is saying. So I want to get rid of inches. I want to end up with feet. I know there are 12 inches in 1 foot. That'll get rid of inches for me. So I take 173.26, I divide by 12. I get 14.4. Right, so fairly straightforward problem, but the takeaway is kind of scary. So this is not a unreasonable measurement for the front hood of an SUV, 40 inches off the ground. But it's saying that you cannot see the 14.5 feet in front of you. You can first see the road past that distance. So anything that is within that first 14.5 feet and, meets those height requirements like we're seeing in the picture, you're not going to see. And you can actually find pictures where they've sat a bunch of kids in front of a parked SUV and the driver cannot see them. That's scary. And what's even kind of more surprising about it is you might think that a large vehicle like an SUV gives you better visibility because it's higher off the ground. It actually typically gives you worse visibility because of how far the nose sticks out relative to a tiny car. So this distance is typically actually smaller for a small car. They have better visibility of the road in front of them. So if you drive a large SUV, I don't mean to freak you out, but just be aware of this and drive carefully. All right, and that is where I will stop today so we can cover the rest and start chapter 2 next time. That will, I hope, be in person because, man, doing this in a recording is not fun, but Anyway, thanks for your patience on that, and hopefully see you in person on Thursday.